Hi! In this video I'm going to show a method you can use to tune the parameters of a PID controller. The method is an open loop tuning method and is called Skogestad's method. We will use the method to control this system, which consists of a wind tunnel with a heating element in one end and a temperature sensor in the other end. Since there is some transport time for the air through the tunnel, the process will get some time delay, which makes it slightly more interesting for controlling. But overall, this process is not very difficult to control. Since the method is an open loop tuning method, we are going to perform an experiment without any feedback at all. Instead, we're going to send in manual values and see how the process responds. Some processes may spin out of control when you remove the feedback, so this method is not suitable for that kind of processes. But temperature does not behave like that. After the experiment, we will look at the signal logs and read out values like, for example, the time delay in the process and other properties. Based on this, we will use the Skogestad's equations to find the correct Kp, Ti and Td parameters. Actually, for this process, we are only going to use the Kp and Ti. The controller parameters are calculated differently for different types of systems. Our system is a first-order system with time delay, so we will use the formulas highlighted. Before we start, I just want to clarify what the parameters in the controller means. The Kp parameters is the gain, and it describes how strong the controller should react to an error. The Ti parameter is there to remove an error which have been present for a long time. The unit is given in seconds, and a low value here will make the Ti part take action quickly. The derivative part of the controller gives a strong output if the process value is changing fast. The Td parameter controls how strong this effect is, and the unit is also given in seconds. As you see from the equation for the PID controller, the Kp parameter is actually involved in all three parts, and this makes the controller a bit easier to control manually. I should also mention that some controllers define their parameters slightly different. They might, for example, use a proportional band instead of the Kp parameters, and some controllers use Ki and Kd instead of the Ti and Td. So for this, the parameters need to be converted. The PID controller we are going to use to tune the temperature system use the equation I showed you, and the controller is run in the software program you see here. This program communicates with an I/O device based on a microcontroller, which then in turn communicates using analog voltages to the physical system. A nice feature of this controller program is that it has a feature which lets me download the historical files as a CSV file, and I can use that when analyzing the system. If you don't have this, you should still be able to follow along as long as you have a graph logging the historical values, and the graph should have units on it. Now it's time to tune the PID controller to get good stability. As you see right now, the red value is close to the set point in blue, but it is very unstable, so here we need to do some tuning. On this kind of process, we don't need the D parameter, so we only need to tune the Kp and Ti parameters. We can do this by trial and error, but now we are going to use the Skogestad method. This method is an open loop tuning method, and we need to set a fixed control signal for the heating element. We then need to wait for the temperature to get stable, and we can then do a step change in the heater power and see how the process responds. Now it seems to have stabilized, so I changed the output from 0 to 3. And now we need to wait for it to stabilize again. This is good, and we can now press Save to CSV to save what we see in the plots to a file. The CSV file looks like this, and I'm going to copy the data into Excel. This data will be used to find the time constant and the time delay of the process, and also to find the steepness of the curve after the step change. I then select all the columns and click on Insert Line Chart. And we see something similar to what we saw earlier. And it also helps to scale the vertical axis correctly. The first thing we can do is to find the time delay, and we can see from the plot that there is some delay from the time where the output was set to 3 to the time we see something happening. So to find this, we can go to the line where the controller output was set on. So now we can count the lines until we see any change in the temperature. And I think that happens around here. So that's 22 cells. And since I know there is 0.1 second per cell, we can do this simple calculation, 0.1 times 22. So the time delay is 2.2 seconds. Next, we can find the time constant. And the time constant is defined as the time it takes for the temperature change to reach 63.2% of the total change. So we should start by finding the total change. We see that the initial temperature is around 26.5, and we can scroll down and see that we end up on around approximately 33.3. So the temperature change was 6.8 degrees. Now we need to multiply this by 0.632 to find how much temperature change there is until the time constant has passed. So I have plotted this as a blue line here. Where these lines cross, that's the time where we find the time constant. We can just look in the values. We need to find how much time is there until we see this value, 30.8. And we need to start counting after this time delay has passed. So that was here. So just count the cells. And as you can see, that's 179 cells. 179 times the time step, which is 0.1. The time constant is 7.9 seconds. The next thing we need is to find the steepest tangent along this curve. So I will try to fit this blue line tangential to this temperature curve. I do that by changing this value, and I just test the different values until I think it's around tangential. I think that's good. 0.438 degrees per second. That's the fastest change. I have collected all the information we have so far, but before we continue, I want to show that there are actually two ways we can calculate the steepest tangent. The first is by reading the tangent off graphically, like we just did. And the second option is to actually divide the time constant with the delta temperature change. And as you see, we get approximately the same value. So you can choose the method you prefer. But for a more complicated system that has more than one time constant internally, there might be a difference. Next, we need to calculate the normalized tangent Ki. And we do this because we used a step change in the controller different from 1. The calculation is done by dividing by the time step u, and we get the value of 0.144. Next, we're going to decide the value Tc, which is the time constant we want the final system with the controller to have. And the usual thing here is to set this equal to the time delay, so we set it to 2.2. Now we only need to apply the formulas for calculating the Kp, the controller gain, and the Ti, the integral time. So we get these two values, and these are the one we are going to put into our PID controller. As you see, the temperature goes to the set point after a set point change, and there are no oscillations, so these parameters seem to work good. Since we have done a step response test on the system, we also have enough information to create a mathematical model of the system that we can use to simulate the system. The only value we are missing is the heater gain, which is the internal gain in the process from the input to the output in a steady state. To calculate that, we need to divide the total change in the temperature by the step change we did. And the result is a gain of 2.27. Here is the differential equation, which describes how much the temperature is changing per time unit. In this, most of the values are constants, but as you see, the u and the t out are the variables that can change. The equation is actually very similar to a general first order system. The only difference is that the u here is not the current u, but we take the u that happened 2.2 seconds ago. And we have also added the room temperature here as a constant. I then converted the differential equation to a transfer function using Laplace transformation. In this, the first part corresponds to the first order system, and the second part corresponds to the time delay. Now we can use the transfer function in the control system library in Python. This is the Python code, and here we first separate the items above and below the fractional line. We then use the control library to create a transfer function. We also create a separate transfer function for the time delay and combine the two into one. We can then finally use the step response function to see how the step response would actually look. When looking at the output plot, we see a typical step response curve for our air heater system, and it should have the correct time delay, time constant, and heater gain. The next step is to simulate the complete control loop and not only the air heater. For that, we need to take into account the transfer function of the low-pass filter, and here we use a filter time constant of 1. And we also need the function for the PI controller. And here we will use the KP and TI settings that we found with the Skogestad method. To combine the transfer functions, we need to first multiply them together to get the loop transfer function, and then we can get a tracking transfer function by doing this. And this transfer function describes how the output temperature reacts to a change in the set point. I have coded the tracking transfer function into Python, and as you see, the process responds fairly good after a set point change. We can also try to decrease the controller gain, like this, and we now see that the response is slightly slower. The code also returns two more plots. The first one is the poles and zeros map, and here the poles are represented by this X symbol. The important thing here is that all the poles are on the left side of the plot center. This means that the system is stable. Since they are also using the imaginary axis, it means that we have some oscillatory motion, and that's confirmed by what we saw. The second plot is a bode plot, which describes more details about the frequency response. The values we are reading off this chart is the gain margin and the phase margin. If these values are small, we have a fast responding system, but it is also close to being unstable. So because of that, we want to have low margins, but not too low. The phase margin can be read off at the frequency where there is no gain in the process. So that's here where the magnitude is crossing 0, which means a gain of 1. And at this frequency we can read off this phase delay, and this value represents how much a sine wave would be delayed if sent through the system at the specific frequency. And the most important thing here is that the gain margin is not 0, because that means a phase lag of 180 degrees, and that means that the controller action comes too late and can instead create bigger oscillations. We usually want a phase margin between 30 and 60 degrees, and in our case we have 44.55 degrees, so this is acceptable. The gain margin can be read off at the frequency where the phase lag is 180 degrees, and that happens here. We then read off the magnitude of the curve up here, and we read a value of 11.78 decibel. And converted to normal gain, that is 3.88. And this means that I can multiply my controller gain by 3.88, and the process will then be marginally stable. This means that oscillations will stay in the system and they will not be increased or damped. So that's the absolute maximum value we can use for our controller, but in practice it's good to have a safety margin, and a factor of 3.88 is reasonable. So that means that our bode plot confirms that our process is reasonably stable and also relatively fast. That's it for this video. Please post your favorite PID tuning methods in the comments and also post any questions. Thanks for watching.